Cool. Everyone, you doing well? You had a good lunch? How are you feeling? Ready for this afternoon? So I'm going to tell you one trick. It's a bit like a one-trick pony talk, this one. And we'll cover two equations, literally 1 hour per equation. How does that feel? And I'm going to talk about deep generative models. And actually, Shakir, if you're here and raise your hand, a lot of what I'm talking about in the last maybe 20, 30 minutes of this talk originates from Shakir as an inventor and first author. So if it's hard, blame him. If you like the idea a lot, which I really do, then I also blame him. Or give him all the credit. When the ideas that I'm going to talk about to you now came about, maybe 2 or 3 years ago, it really pushed a shift in the way people thought about many algorithms, including expectation maximization from the 1970s. If you followed the Bayesian inference variational-based literature in the 90s, it really caused a sort of almost a phase transition in the way people do Bayesian modeling. So I'll speak about generative models. So let's just see if this works. So what do I mean by generative models in this case? So generative models, I basically mean that we have data, and we want to model the probability distribution of data points. So it's unsupervised learning. So if you're able to do that, if you're able to learn a density from data, you can generate samples from the data. You'd know whether a data point is an outlier. You might be able to fill in missing values, etc. Deep, you've covered a lot. There'll be lots of deep networks in the middle. And then models, it's kind of obvious. It's just a mathematical model. So I'm going to ask you to please maybe get a pencil and a piece of paper for this lecture, because this will be a very interactive lecture. Please just raise your pencils and a piece of paper. So first, our first question is a 2-minute exercise. So pretend you're a data scientist in a company, and I come to you as a client, and I present you with this data set that you've never seen before. Okay? It's not the MNIST data set. This is Ulrich's data set. Take 2 minutes and tell your buddy everything you can about this data. You're a data scientist. Okay. Let's take 2 minutes. What do you see? Okay, shall we get some feedback? What are properties of this data set? Anyone raise your hands? Yes? No, there are 10 data points. This number here, that's my data point index. I have 10 data points. Okay. Any other ideas? Come on, don't be shy. Data scientists? If you guys were a startup, I would never buy a product. Come on, interact with me. Yes? Sorry?
The second column appears twice as frequently.
Okay, the second column appears twice as frequently as all the other columns. Any more suggestions? Okay, there's always a white line. There, etc. Okay, more. Okay, so I never told you if it's temporal or not. Okay, anything more? Same columns, yes. Oh, different shade of gray. Oh, someone spotted there might be a different shade of gray in there. Anything else?
It only goes to the first row by x9. Oh, no, sorry.
Yeah, okay. Who spotted that we have 16-dimensional inputs? Okay, great. Okay, so everyone. So you've got a question. Maybe X is 16-dimensional inputs. Maybe, so this R16 is a 16-dimensional real valued if you were to like stack all the pixels. Would anyone have said that X is in 0, 1 to the power of 16, so binary, maybe, if the screen projector did not work very well? That's another option. Data could be binary, etc. Okay, so the main thing I want to point out here is that there's a property of this data, and that is, someone said, there's a column. Every image has a column that's shared, and I can, if I told you the column number, you would be able to, with really high accuracy, generate the image. Okay? If I told you a number 2, you could go and you can draw the image on a piece of paper. Are you all cool with that? So, there's something hidden in here, which is the idea of, I'll just write it here because it's so fundamental. It's compression. The idea of compression is that from this number 2, you can generate an image. Alternatively, if I give you any image, you can write the number 2 down. So for instance, if you are paying really a lot of money for your mobile bandwidth and you need to send an image to someone, you can send a text with the number 2, and they'd be able to decode the image on the other side, and you wouldn't have to pay a lot of money. Okay, so that's the idea of compression that's hidden in here. The other idea is that maybe there's a data manifold. So I can capture most of the variability in the data that I've shown you through one number. So for every data point n, so n is my data point index, I can assign a number z, which is 1, 2, 3, or 4, and based on that number, you can write down your own little rendering algorithm that will decode or decompress it into an image. Okay. So how do you do that? If you were to write a little algorithm in Python, you might have a model that will do the following. It will take as input z, and of course z's a variable, so now it's 2. And there might be some little for loop bar drawing process that will push this image out onto your screen. Okay? So it's very simple. Voila. I give you Zn equals 2. You write your own algorithm, and now you've got your image xn. So here we go from a one-dimensional thing as an input to a function, and you've got a 16-dimensional thing, which is like either 0, 1 in 16 dimensions or a real number in 16 dimensions, or whatever, as output. Okay, but we're not here to study algorithms and do things by hand. So we want to learn this. So another idea is that maybe instead of writing an algorithm that takes this number z equals 2 and draws an image with a bar in column 2, maybe you can write down some neural network with parameters that will take as input a one-dimensional quantity, which is z, which is 2, and it will emit as output a 16-dimensional vector, which is your image. So your homework now for the next 2 minutes, or 3 minutes, is to write down on a piece of paper what that neural network would be if you were to implement it. If I told you I want an algorithm that draws images like this. Okay, away you go. I see some people are great visualizers. You draw the picture in your heads. They're laying the course here. I want to see some pictures. No loafing from the organizers. Come, come. Okay, everyone, so we quickly regroup. In your neural network, multi-layer perceptron that you drew, do you all have a one-dimensional input? Do you all have a 16-dimensional output? Okay. Who drew a convnet or deconvolutional network? Raise your hands. One or two or three people. Who decided to use a multi-layer perceptron? Okay, more of you. Who decided to use a single-layer model? Okay, we've got some single-layer models here. Who decided to, I don't know, invent something else? Okay, other inventions as well. So now in your drawing, try to circle all the parameters theta that you could change or tweak to generate this image at the bottom. Okay, just to tell you what these theta parameters are, let's imagine we do a multi-layer perceptron and we take a one-dimensional z as input, and I've got a total of 16 output units for my image x. Maybe I decide on a hidden layer of 5. I might have a weight matrix that blows the sky up, so there's a weight matrix for the first layer. Maybe I have a weight matrix that I multiply with the output of that guy, so I've got a weight matrix for the second layer. Maybe I add a bias unit, so there might be a 1, and there might be a bias that gets added there, so that's the bias for the first layer. Maybe I would add a bias here for the second layer. I mean, this is just my little design. You would have your own one. So if I speak about theta in this talk, I would refer to these weights, these biases, and these biases. Okay? And that would be whatever you have on your design. Okay, so now we get to the idea of a data manifold. So now forget about the idea that that z is just 1, 2, 3, and 4, like an integer. So imagine that I could make z a real number, just for the purposes of this talk. And I have a process that would take in a number that is somewhere on the real line. I would just call it 1 for now. It doesn't actually have to be 1. And then my network with parameters theta would draw it, and it would draw an image with a column. The first column being white. Second one is if I have another z that's very close to that z, I would have, if my neural network learned, I would follow that line, and I'd draw an image with the first column being 1. So the idea of a data manifold, which Alta mentioned, is that it's really like a sheet of paper. So you can imagine this line that I show you being a piece of string in a 16-dimensional space. So my 16-dimensional image actually lives on a one-dimensional manifold, and that manifold just tells me in which column to draw the white bar. Okay? And there is, as someone rightly pointed out, there is some noise in the generative process. So I do not only draw a bar, I would also maybe add some noise to the pixel, so you account for mistakes. Are you all happy with this idea of what a data manifold is, and how I can go from manifold to images? Cool. So now that you have a manifold, I did mention what the idea of noise is. The idea of noise is that for similar values, I might decode it to slightly different images because there's noise in the process. It also means that, and that was a question that was in Constantina's talk this morning, that if I have the same point z over here, then this point, hang on, let's try this one. That point z might generate that image with some small probability, but this point z might also generate that point, or that image with some small probability. And the reason is that I add noise to the process. So if I added noise, might have a template image, and the kind of noise would either flip me to that image or that image. Okay? So we generate the images on from a manifold, and we add some noise. Okay, so since images are noisy, I'm going to ask you to change your network a tiny bit. And what you're going to do now is, instead of just generating a single image with no noise, I want you to think about the way in which you can add noise at the bottom. So let's just do this. Add some noise at the bottom so that you can either get that image or that image. Now, the reason why we do this, and just to clarify notation, is I would start with Z at the top. So this notation is conditional on seeing Z. I have a probability distribution over all images. And this set of theta parameters are just the parameters that we train to try and decode the Z. So it's a conditional distribution of image given Z. Okay, see if you can find a way to generate noisy images from Z. Okay, can we quickly recap? So I'll give you my solution in this case. So I'm assuming that my images are binary, so every pixel is either 0 or 1, and there are 16 of them. In the last layer of your network, you'd have an activation A for every unit. And what I care about is, of course, if there's 16 pixels, I care about pixel I. And I might say that the probability of pixel I being 1, or turned on, or being of a certain class, given Z, which is the input at the top, and all my parameters theta, which I sort of decoded it, up to my last activation A, which would be the number that comes out of that unit. That could be, for instance, I don't know, a sigmoid, a logistic function, 1 over 1 plus e to the minus my activation for unit I. So that means that that gives me a probability distribution of pixel I in this image being white or black. Okay? So if I can do that, I can actually sample different images from this binary Bernoulli distribution. So this brings us to the idea of a decoder. Yes?
Where would the randomness come in there?
Oh, okay. Where would So randomness comes in because the probability of pixel I being 1, given Z, and all my parameters theta, that is a sigmoid. It's 1 plus e to the minus activation I. Okay? If I were to draw this sigmoid function, what does it look like? I have an axis over here, and this axis is activation I, and the probability distribution, which is this this function here, is a sigmoid that runs from 0 all the way up to, well, actually up to 1. And of course, if my activation is really big, I would get a number that's very close to 1. So I would flip a coin. And well, actually, I draw a random number between 0 and 1. If the number is less than 0.9, so let's say that's 0.9, I color the pixel black. If it's less than 0.9, I color the pixel white. If my random number is between 0.9 and 1, I would color the pixel black. So you see that if the activation's If the activation is positive, really positive, the odds become much bigger for the pixel to be white. If the activation is way to the negative side, the odds are much bigger for me to color the pixel black. Of course, if all my activations are exactly 0, then it'll look like one of those old TV screens where I just generate white and black noise. So of course, what I want is a network for which my activations would be big, where I expect white pixels to be, and it would be very negative, where I expect black pixels to be in this toy data set. Okay, any more questions?
If you're talking about flipping a coin, what does it do?
Sorry, it's flipping a coin with heads. The odds of heads is 0.9. So it's like it's a weighted coin. It's the kind you really want to gamble with. Okay, so the idea here is that we have a decoder. So I send Z, I write down on a piece of paper, and someone has a network that takes this low-dimensional Z and blows it up into this image. In the practical this afternoon, it'll be called a generative network. So this generates images. It generates images because I give you Z, and it generates X. Okay. That's the idea for decoder. Now I'm going to ask you a really tricky question. So the decoder tells me that I know Z, and I can draw images X. Okay, it goes from Z all the way to X. If I now tell you that I give you X, so I give you this image, and I ask you what the values of Z was, how on earth would you answer that? So what I'm really, really asking you here is that you drew a very complicated model with a large number of parameters, theta, that drew an image X, and you can do the downward computation. You can go from Z to X. Now I want you to do the opposite. I want you to take X. I give you X. This is the image. And I ask you which Zs could have generated this X. Yes? Z is a hash code, yes. Well, it's a noisy hash code, one-dimensional hash code. Okay, do you think this is an easy problem to solve? No, of course it's not an easy problem to solve. That's why there are 50 more slides. Yes? Okay, we've got a very, very cool idea here. Okay, so the idea is that I fix my weights. And then I try different values of Z up here, basically from a prior, and then I basically see which X's I get. And the number of X's that I hit from certain Zs, that would tell me which Z would have generated it. That's a very good idea. In Monte Carlo method, it's called importance sampling, or actually rejection sampling. You reject Zs that don't generate the data that you've seen. The problem with that idea, it's a really cool idea, but if we were to go to very high dimensions, for instance, and I had a latent code that was not just one number, that was like 20-dimensional, then I might have 2 to the 20 or a really an exponential number of things that I need to try to hit X. And of course, the odds of actually ever randomly being lucky is so small that the universe will end before we get there. Yeah? Yes, okay, we'll do that. We are going to do that. So the two big problems in statistical inference, at least in Bayesian inference, are these. It is that you would write down a likelihood, and I give you X and all your weights, as you've just mentioned, and I ask you what was Z. If you remember Constantina's talk, the question would be, what is the posterior distribution of Z given X? So that's one problem that we really like to solve. The second one is, you somehow have to magically learn all these weights that take some random X and generates images. So the two problems is one of inference. How do I find my latent code given my image? And the second one is, how do I learn my network parameters, theta? Okay. The problem with inference is the following, is that people speak different languages. So maybe here at WITS, you have a secret pact amongst yourselves that your latent code would be in the order 1, 2, 3, 4, or 5. And maybe at UCT, there's another secret pact that you are going to scale your latent code to be on a really small scale. Maybe all our foreign visitors would have another secret pact to fool us that you're going to add 100,000 to every number, and you can still, from these numbers, find a way to decode and draw the white bar in the right place. So actually, if you know that, it's pretty much impossible to figure out what Z would have been, unless you know basically the local lingo, the way people would have specified where the Zs would have lied. So the point here is that there's no way that I can answer any question about Z unless I tell you something about where I think Z would have lived before you saw any data. Okay, so you really need a prior. So assumption, well, the key point is to really answer that question, we need some notion of where we might need have started. And for anything, you can't do inference unless you have prior assumptions. It's true for deep learning, it's true for Bayesian inference. Okay, so how do we encode this prior? These prior assumptions, okay? You could do anything, really, with a prior. I mean, if you have a number 0, 1, 2, 3, 4, 5, you can have a prior that says this is a discrete thing. For reasons that will become apparent later, it's usually computational convenience, I'm going to take a prior that's Gaussian, and this just says the mean of the Gaussian is 0, and the variance is 1. And the beautiful thing about the Gaussian is that I can compute the area underneath the Gaussian curve. If you don't know how to compute it, you can Google it. It's one very short expression. Okay, so the area is always 1 underneath this prior curve of mine. That's the important thing to notice. The next distinction that I'm going to make here is that there are two kinds of variables at play. The one is the unobserved variable, the latent code that would have generated the image. And the next one would be a set of observed random variables, which would be all these images. Right? So I've just given you a prior over Z, and I might sample from that prior, and if I'm really lucky, I can decode those into images. Are you all happy with this idea of a prior? All that the prior says is, I want to have some distribution of where I think you would have started. Now, this does not need to be the prior. If you really wanted to, and you wanted to take our international friends' way, who said our Zs all have a mean of 1,000 and a standard deviation of 1 or 2, you could have done that as well. Okay, you should just have something that normalizes. It's to 1. Now, here's the idea of inference. So I give you X, and you keep your parameters fixed in network. What was Z? Let's cancel that. And there might be more than one Z in this space that could have decoded to my image. So, as a 3-minute exercise, I'm going to ask you to draw the joint density. So let's make some assumptions before we do this exercise. So in this exercise, I'm assuming that the largest likelihood of an image is 1. 1 just means I was extremely lucky and I got all my pixels correct. So the largest value of P of X given Z is 1, and I've just drawn my prior. So can you now draw the joint density, which is prior times likelihood, as a function of Z on this axis? I mean, on this axis over here. See if you can do that. Hey, have you all had a chance to try? Not yet? A few more minutes? Okay, so my clue for this exercise is the largest likelihood value is 1. So that should sort of tell you what the function might look like. Next clue for the exercise is maybe that all of these sets decode to images of bars that are either off the charts or they're in bar in place 4 or 3. Okay, so let's start on this end over here. If I pick this Z over here, can you imagine it ever generating a nice image with the bar of 2 in the right place? No. Over here? No. Over here? No. Over here? No. Over here? Yeah, maybe. Okay, over here? Maybe. Over here? No, that generates bars in position column 3. There, not either. Okay, and the maximum value is 1, so let's imagine it does a pretty good job. So what you can expect is a function that sort of sits over there. Would you agree? Yes?
Didn't you introduce the manifold where like the mapping is really not as simple as that? How do you know that Z's that are close to that mean of that likelihood creatures not actually mapping to the same?
Okay, there's a very, very good question which I preemptively should have mentioned. How do I know that the Z's here, the Z's here, actually map to the right X's? When I initialize my model, of course, it will totally not map to the right X's. The manifold will be all over the place. If I manage to actually learn the data manifold, which I've sort of given you here, then the right X's that are Z's that are close would all generate the same image. So in the second part of this talk, we're going to figure out how on earth we learn these thetas. So imagine that a generative model is great. It just if I tell it to 2, it's going to generate an image in position 2. Okay, just for now. Okay, so the joint density looks like this green one. Now, I have another challenge for you. I told you that the area under the prior curve is equal to 1. Can you give me an expression for the area under this green curve? How, if I asked you that sounds like, what's this red area called? What's its value? What would it be? Okay, it's clearly less than 1 because the big area is equal to 1. Yes?
1 minus the sum of the other conditional probabilities.
Okay, so you can go 1 minus. Okay, what if you were to compute it directly? Do you think you can do that? Okay, so I've asked you what the area is, and this area is actually unknown, right? So the area under this curve that I've shown you is just the density of my data averaged over all possible assignments of my prior. So the green curve that we wrote is the red curve multiplied by something that's going to downscale it, and it's going to downscale it proportional to how much it can actually decode. And this expression is just another way of writing the joint density. Konstantina mentioned Bayesian marginalization, which basically just, this integral just says I get rid of Z, and all I have is the probability of generating data averaged over all possible prior assignments with my neural network. Do you need the moment to digest that? Okay? Yes? Okay. How did I get the green curve? So I made an assumption that I made an assumption that I had thetas that actually really modeled my data well. So the assumption was that for z's that are in a certain range, I would generate a bar in column 2. And this is just like a magical neural network setting that we're going to learn a bit later. Because this thing is high, whenever z actually is able to decode into the image that I see, and it's going to be almost 0 when it decodes into junk, I multiply something that's really big in this area, capped at 1, with this Gaussian prior. And that's the joint density that I get at the bottom. Does that sort of answer your question? Okay. So I told you how to compute the area under the curve. So the area under the curve here is called my marginal likelihood. And the big word you need to remember here is the evidence. It's the evidence of the data over all prior settings. Okay. Now, here's Bayes' theorem for you. I told you that this area is really hard to compute, this green one. Oh, sorry for the iPad. I told you that area is really hard to compute. So here's Bayes' theorem for you. The green curve that we wrote is the likelihood times the prior, so my joint density. We also computed the area under the green curve, which was this marginal likelihood or evidence that we just computed. And the posterior density, after seeing x, is just the green curve scaled so that its area is 1 again. So that's Bayes' theorem for you. You just rescale your curve so that your area is 1 under the curve. Okay, so now I can actually write down an expression for the evidence or the likelihood of all my data points. So remember we had 10 points, and I've just shown you the likelihood or the evidence for 1 point. So if I let this capital X denote all 10 data points, then I'm assuming here that my 10 data points, the 10 images that I see, are completely independent. So my likelihood could be the product of all 10 images, n equals 1 to 10, and it's just the likelihood of image 1, 2, 3, all the way up to 10. If I take the log of the likelihood of all my data just gets rid of the nasty product, and it turns it into a sum, and the log sits over there. So this is the kind of quantity we want to maximize. If I want to maximize the likelihood of seeing my data, I want to maximize this expression over theta. The only caveat is that I can't do that. I can't do that because I can't compute this area under the green curve. So what we're trying to do in pictures, and this is the best way I can explain it to myself, is that every data point that I've seen, 1, 2, all the way up to 10, has some evidence, or it has some unnormalized joint density, right? So it's basically the sum of the logs of those areas. And what I want to do in pictures from a really, really, really high level in mathematics is to make, if I want to maximize this guy, I really want to make the area under these green curves, the sum of the product of areas, as big as possible. Because that would maximize my data likelihood. You all have sort of get how this picture corresponds to the math we want to do. Yes? No? Happy? Are you with me? Yes. Okay. Now, here's a fun question. What happens in this purple area, and what happens in the orange area? So when we generated images, there was a whole area of my prior in Z that would generate junk images. Okay? And there's a whole area here that's probably not explained either. And The idea of generating junk images, because none of these z's actually decode the images that I see, means that whatever mapping I've learned does not capture the entire data manifold. So I would sample some z's and I would decode them essentially into noise. So the way we're going to get this quantity bigger would essentially be to shift these to the right a little bit and to maybe change theta so that they become taller. So that is the idea of capturing a data manifold with unsupervised learning. So a great solution would look like this one, where I've essentially stretched out my space in Z, and all my Zs from this end in my prior to that end could all decode into images that I've actually seen in real life. So that's what we're after. So I'm wondering if we should not take, let me just see what the next bit is. Okay, let's just do one or two more things. Someone mentioned earlier that there are twice as many bars in the second column than there are. Who was that? Very, very, very good observation. I didn't think anyone would see it. That's why I said for the sharp-sighted. So if you think of these kinds of images covering 40% of your image space, what I would want is 40% of my mass in the Zs, in my code, should be able to decode to images with a bar in the second position. Because then I've really, really captured the data manifold and the density of my data. Then, of course, 20%, 20%, 20% would decode to the other parts of my images. Okay, so we said that if we want to learn this, we want to maximize the log likelihood. So it's maximize the sum of the contributions of every point. And each of these is just the area for every data point. So before we get to the hard part, I think we should maybe take just a 2-minute breather, and then you can sharpen your mathematical pencils. And if you have any questions up to just this point, just ask them. Okay, maybe 5-minute breather. Only 5 minutes, not 15. Yeah, it's gonna. Well, you can generate quite a model that does that. You can just write down a likelihood for this. What to do. Give me a sec. What you say? Prior on. What's the posterior there? You write down the joint. It's like the next one. So you can't ever go above it. Product of likelihoods for data. Points.
Does Microsoft really on in its buttons?
It's not so easier to maximize, so much maximize. But I get what you mean. Everyone, are you ready to restart? Okay, let's start. So before the quick break, we said that we want to maximize the log likelihood, which is the log likelihood of every data point. So for the next part, I'm going to remove superscript n, and I'll just look at one term in this log likelihood sum over all data points. So I know that this quantity here is actually something I can't compute analytically. I can't write an expression for it. I can't really get gradients for it because it's the inverse. It's literally the inverse of a neural network. Neural network is one way. This is the inverse of a neural network. And there's a whole array of things you can, like techniques you can throw at this problem. There's the Monte Carlo methods, the deterministic approximate method. So that's just for reference. I'll just show you one deterministic method to do this. Okay. I do apologize. The next section might be slightly math heavy, but I'll go through it really slowly so that it's as clear as possible. So the kind of term we really care about computing is the log likelihood, which is an average over the prior. So we want to compute this integral over here. And I can't. There's no way I can do it. So I can't compute the integral. But what I can do is I can try and approximate it as best as possible. So the next section will be on how to take an integral, which is an integration problem, and turn it into an optimization problem. Okay, so the idea here is something that's called a variational lower bound. So I'll slowly talk you through the slide. So we wrote down some green curve, which was the unnormalized posterior distribution. I also told you that there's no way I can tractably compute the area under the green curve. So I can't actually get that. I'm going to create a setup where I find another function q with a totally different set of parameters. It's also going to take x as input, and it's going to emit one-dimensional value z. Remember, this z is one-dimensional, R1. You know that you can compute the area under a Gaussian curve. You can go to Wikipedia, you can get the analytic expression. So I'm going to construct a way where this Q, which is a Gaussian distribution without its normalizer, will sit tightly under any kind of green curve, guaranteed. Okay? So the idea of a variational lower bound is that I can't compute this crazy area over here because I just don't know how to do it. But I know that I can compute some scaled version of a Gaussian, and that I can compute. So let's flip to the bit here. So what I'm doing is, instead of reversing the process, remember I told you that x is here and I want to reverse the process from that side. Instead of reversing this process, I'm going to take my x and I'm going to paste it on the other side, and I'm going to call it an encoder. Now, the quantity I was really interested in was the posterior density of z given x, which went that way, and I'm going to just use this guy, which is a deep neural network, as an approximation for this reverse process. So in the practical, you'll see something that's called an inference network that will take x as an input, and it's going to output a mean and a variance of that Gaussian. Okay, so if you were to write this reverse process with a completely different set of parameters as a neural network, it should take x in, and it should output a Gaussian with a mean and the variance. And the mean is, of course, a function of the input with all my neural network parameters. And the variance of that Gaussian is a function of my input with my deep network parameters. So this thing is called an inference network, or it's also called an encoder. So there is that I encode something here, and I decode something here, and there's a lot of noise in the middle. So that's the whole process. I would have an encoder and decoder with a small z or code in the middle. And I want to learn this process end to end. Okay, so maybe I'll first read this very slowly and then give you my interpretation, and then we'll go through it again. So my strategy is that I have a green curve that I can't compute. I can't compute its area, but I want to make this area as big as possible. I also know that I have some parameters phi that tuck underneath this green curve. So what I'm going to do is I'm going to try and inflate this, and by inflating it as big as possible, I can also inflate the green curve to sit above the blue curve. And that's my strategy for getting the green curve really big. So my response is, what on earth is going on here? So I'll repeat it slowly, and then we'll go through the math, and maybe it will make sense. If this is your gut reaction, that's perfectly normal. Okay. So I have two parts that I'm going to train. I'm going to train an encoder that's going to try and inflate this. So I'm going to have parameters of my encoder. So these are my encoder parameters. That's going to inflate the area of the blue curve. How do I inflate this area? Well, it's really easy. I can inflate it by shifting the mean that way and maybe making the variance a little bit bigger. So inflate this area by looking at my mean and my variance encoding. Okay. So as a 3-minute exercise that I'd like to do now is to write down some neural network that will take in x as a 16-dimensional input, and it should emit a Gaussian probability distribution of a 1-dimensional code. As a hint, this Gaussian has 2 parameters, so your network should emit 2 numbers. It should emit a mean and a variance. And then you should tell me what your parameters are. Okay, have a go and see if you can write an encoder. Okay, everyone, can we regather? Let's do a quick straw poll. Who has a one-layer neural network as an encoder? Who has a convnet? One. How many more convnets? 2, 3 convnets. Who has a multi-layer perceptron? Who has 2 layers in the drawing? Okay. Right. Okay. Next question. Your variance is always non-negative. Whose variance is non-negative? Can you prove that? Who has an output that has a negative variance? Okay. Who has a mean that's either positive or negative? Okay. Who put a tan h? Hang on. Who put a sigmoid function as the last step to emit your mean? Did anyone do that? Because your mean can't be between 0 and 1. It's a real value. It has to be linear. Cool. So let's try a version. So you have a 16-dimensional X that comes in. You can have any multi-layer perceptron with weights and biases. And maybe at the very end, you want to emit 2 numbers. Not one. One would be your mean. Next one would be your standard deviation, or the log of the standard deviation. So you do something like this. The only tricky bit is that this value, your standard deviation, has to be non-negative. You can do many things. One way is to not parameterize your variance as the variance, but actually parameterize it as the log variance. And so your activation is the log variance, and your variance is then e to the activation, for instance. That's one way you can get around it. In the prac, you'll see another way around it. Okay, so I'm going to, yes? Yeah, you can do whatever you like. I mean, you can have one neural network that gives you the mean, one neural network that gives you the variance. That's totally fine as well. I've seen both. I've seen implementations where you have 2 networks. I've seen implementations where all the weights are shared up to the last layer, and then you just spit out the mean and the variance. Yeah, that's a very open question. The independence assumption is a bit weak. The fact that you have a Gaussian distribution, I mean, that's also not realistic. At the end of your prac, you'll see 5 or 6 totally open questions that you can speak to your buddies about, and that's one of them. But that we don't have super clear answers for. Okay, I'm going to give you a sneak preview of the objective function that we're going to derive. Okay, so the objective function says a few things. The objective function, before we derive it, says that I have 2 networks. I have my encoding network and my decoding network. I'm going to take my log likelihood of my encoding network, and I'm going to evaluate it over all the possible z's that my, I'm going to take the log likelihood of my decoding network, and I'm going to evaluate it over all possible z's that my encoding network is going to spit out, right? So I'm going to take, so this encoding network gives me a distribution over z, like lots of different values of z, and I'm going to evaluate the log of this guy over all possible values that my encoder can give me. So that is the first expression. Maybe there's some notation that's not very familiar to you that we'll cover in the next bit. If you ever see something that's like a crazy capital E, this thing basically means an expectation. And it's an expectation because it's an average. If you see a subscript thing like this, it means the expectation over a certain distribution. So it's the expectation over taking x and emitting z. The next term in my objective function is called the Kullback-Leibler divergence. It basically measures how different two distributions are. So why is that necessary? It's necessary because when I told you what a great solution would have looked like in here, right? A great solution would have been one where all my green curves are sort of spread out as far as possible and as close as possible to the red. Okay? So the KL divergence between two Gaussian distributions is 0 when the green curve is exactly on top of the red curve. So that's what this KL term does. The other term, so of course, if there's only a KL divergence term, then the solution would have been to take all the green curves and make them whoppingly big and be exactly equal to the prior. But of course, that's really bad because none of them would be able to capture any of the data because we want the 1s to be there, the 2s to be there, and there's the 3s to be there. So there are two different terms that essentially fight with each other for dominance in some way. There's one term, which is the KL term, which tries to get as close as possible to the priors. It wants to make these guys fatter. And there's a term that tries to generate my data, and they essentially try to make these areas narrower. Okay, so that's the intuition of the objective function that we'll derive. Okay, we did the what? Okay, now, the other thing is that the KL term is always non-negative. Cool. So what we want is a way to differentiate and run this thing end to end. Okay, now sit on your seats. Sit on your seats. It's probably the longest equation you're going to see this whole Indaba, and I'll walk through it very, very slowly. And I'll do it step by step. So the first step is to take the log density of x, which we expand as the prior times the likelihood. And we need to, so this expression over here is just a function of my theta. It's a function of my network that takes x, z, and it throws out x. So it's a function of my decoder. Problem is I need to include my encoder in the game. A very sneaky trick would be to multiply and divide by the encoder. So this expression here still gives me this green area, okay? So the sneaky trick that we do is to multiply and divide by the encoding network. So now we have an expression that depends on theta. So theta takes z and it emits x. And we have an expression that depends on my encoder, which takes x and it spits out z with parameters phi. Okay? Now there's a next step, which is called Jensen's inequality. Now before I do Jensen's inequality, maybe I should show you Jensen's inequality on paper. So as a 3-minute exercise, draw log as a function. You all know what log looks like. It starts at the bottom and it goes up. And convince yourself that this expression on the whiteboard is true. Okay? I want to see you try it before I give the answer because it will really help you digest how this loss function is put together. The guys at the back knows what's coming for them. Okay, just a quick second. So why is there Z1 and a Z2? So log will be a function of Z. And this is my Z, this will be my Z-axis. And of course, log's only valid for positive Z. So log looks like this. And there will be a Z2 value and a Z1 value. So Z1 and Z2 are just 2 points on the Z-axis. Okay. So knowing that, try and convince yourself that this is still true. Okay, are we ready? So I must confess that this is a very constructed exercise, and I cheated ever so slightly because 2/3 plus a third is equal to 1, and 2/3 plus a third is equal to 1, and these two are all non-negative numbers. So that might have helped you or not. Here's my solution. So I would draw this red line as log of z. Then I would put Z1 and Z2 as any points. The log of 2/3 times Z1 plus a third times Z2 is sort of halfway between Z1 and Z2. So that's like 2/3 of the way towards Z1 and a third of the way towards Z2. So that point, the log is that green dot. On the right-hand side, I have 2/3 of the log of Z1. So the log of Z1 is this point over here. And the log of Z2 is this point over here. And 2/3, like 2/3 of the way from this point all the way to this point gives me this green dot. So basically, this green point is always guaranteed to be bigger than that green point as an evaluation. And it's going to be equal if Z1 is equal to Z2. Okay. So you can see this 2/3 and a third as an expectation. How do I compute an expectation? Expectation of some quantity, let's say that has only two values, would be the probability of the first thing, which might be 2/3 times the value, plus the probability of the second thing times its value. So what I sort of have over here is the log of the expected value of z, or it could actually be log of the expected value of some function of z. Okay? On this side, I have 2/3 plus a third of something. So on this side, I have essentially the expected value of log of either z or some function of z. So I've just shown you a little tiny sketch that proved something called Jensen's inequality, which basically says this guy is, as an expression, is always bigger than that guy. So why is this necessary? Remember a little bit earlier I told you that we want to bound this very complicated integral with something that's really easy to compute, or easier to compute. What I'm doing here is I have instead of 2/3 and a third, and a sum of two things, I've got a sum of infinitely many things, and this Q is just 2/3 or a third, or it's a distribution. And in the same way that I've swapped the log from outside the expectation to inside the expectation with a greater equal sign in Jensen's inequality, I've just swapped the log from outside the expectation to inside the expectation. Does that make sense to you intuitively? Okay, so what I have now is instead of having a log of some integral, I have an integral with some log inside. So you've done the 3-minute exercise. Now the last part of getting to an objective function. So we've done this bit, we've done this bit. I told you you can multiply and divide by the same function. I've shown you why, how we could get a lower bound. And now I can expand this lower bound. So I expand it. So log of A times B is log of A plus log of B. You remember that from first year calculus or metric math. What else do I know? Log of A over B is equal to log of A minus log of B. Right? So if the B's at the bottom, we minus. Cool. So what we do here is we have a log of, come on, I'm a novice in an iPad. We have a log of three things, two things that are multiplied and one thing that's divided. So I take the first thing and I do the log of A times B is log of A plus the rest. So this is where this first log of A comes from, essentially. And the next two terms, those two, all go in there. And what I've written down essentially is this really crazy but very useful objective function, which I've already explained, which has two terms. It has something that's called a reconstruction error, which basically says, on average, if I take X and I push out Z, how well is X reconstructed from Z? If this score is high, that score, I'm doing great in reconstructing. I'm great in generating images. The second term is what's a KL divergence. I mean, you can look in Wikipedia if you want to know a little bit more about these KL divergence things. But it measures how far my encoder differs from my prior. Cool. So if you know the terms scale divergence and reconstruction error, you've reached the first equation that we wanted to compute. So this is the thing you're going to maximize in your prac, and it's already written, and you can just press run and see if you can figure out how all these mechanics sit together. Okay. If I want to compute this expected log likelihood, I mean, that's still a pretty crazy thing to compute. And do you remember when you did stochastic gradient descent? You took subsamples from your data, and so in your first prac or second prac, you had an MNIST data set that was big, and your loss function was defined over the entire data set, and you subsampled from the data, and then took gradients. You remember that? Because it's a massively complicated loss function, and you broke it down into easier parts stochastically. So in the same way, I'm going to subsample sample from my encoding network and then evaluate my loss on that side. Okay, so let's do this. So how do I sample from my encoding network? I take an image X and I push it through my encoder, and it will give me a mean and a variance of a Gaussian. It could be big, it could be small, the mean could be anywhere. And then I draw a number of samples from this Gaussian distribution. So I can do that. Then, once I've done it, just bear with me very slowly. Once I've done it, I can plug those samples in to estimate my function that I get. Okay. So the way I estimate it would, can you still hear me? Yes, would look like this. So this is the quantity I care about. This is exactly equal to sampling lots of samples from my encoding network, which takes X, gives a mean and a variance. So I take lots of samples from this, and I still compute this log likelihood. A Monte Carlo estimate would take all these samples, and it would just plug it in there and take the average. So in your prac, you had something called TensorFlow.reduceMean, which was the mean of lots of samples from a batch. This is exactly the same. I take sort of like a batch sample of encodings, and I plug in the samples in there. So the last 2 or 3 minutes, I'm going to tell you just how you can evaluate this in practice. And the second big trick we're going to do in the practical, and you might hate me for this, but bear with me. If we were to employ this strategy, we could actually compute this. But there's a big flaw in this reasoning, and the flaw is that I can't run through my network, get gradients, and back propagate all the way to the end. Okay? I'll slowly repeat it. If I were to employ this strategy, there's no way I can start with an image, run it through my network, go to Z, decode it, and then back propagate through Z and get gradients. Why can't I do that? The reason is that this sample that I draw from my encoder actually hides these two parameters. I hope I have a picture here. Yeah, I do. Okay. So what happens with this kind of computation is that I can compute everything forward. I can actually compute my loss, but because the loss has lots of deterministic things in the middle, that hides that are samples, I can't get derivatives any further than the samples in the middle. So to sort of rephrase what we try to do is we would take an image, we would get Q phi of Z given X, which is Gaussian. Then I would draw a load of Gaussians from that set. Each of them would be decoded for separate loss, because it's stochastic. I would take the average, so I get my loss estimate, and then I try to backpropagate, and because they're samples, there's no way my gradients can go all the way through. So the big trick that I want to share with you is called the reparameterization trick. And what we're going to do in the next few slides, and then we're done, then I'll open the floor for questions, is this. We are going to find a way to get rid of these encoding parameters in my expectation. So reparameterization works this way. So instead of drawing samples from a Gaussian with a mean mu of x and variance sigma squared of x, that depends on my neural network, I can find another way to draw samples. And the way I draw samples is to draw Gaussian 0, 1 samples and then transform them. Okay? So I draw I draw the same number of samples from a Gaussian distribution with a mean of 0 and a variance of 1. And then I would, depending on whatever my variance was, I would either expand the samples or I'd shrink them. And once I've done that, I would offset them by the right mean. So actually what I have through this kind of transformation is samples from this blue curve, which I obtained by transforming samples from this green curve. Right. But effectively, the samples Z from this curve are exactly the same samples that you had in the previous slide. Are you happy with this idea of reparameterization? So instead of taking samples directly, I take noise, and I sort of transform it to look like the samples that I care about. Okay, second last slide, and then we're done. So instead of having an expectation over my encoder, taking X and getting distribution over Z and sampling, I'll have an expectation over essentially white noise. And then I take that white noise, I multiply it by my standard deviation, so that's my white noise bit, and I add the mean, and that's my value of Z. So my Z is just some white noise transformed. So this expression over here is exactly the same stochastic estimate that we had before, except for one difference. My noise is injected from outside my neural network. So, big take-home message here for the reparameterization trick is that my noise is injected from outside my computation graph, which basically means that I can evaluate the objective function that I could do earlier, but now I can also take derivatives and get gradients. And we all love gradients because we get them for free from TensorFlow, and we can do end-to-end learning. Okay, so the reparameterization trick, just to recap, allows me to do forward computation, introduce noise here that's external to my computation graph, and take derivatives all the way back. So I can do an end-to-end learning for my encoder's parameters, which you drew, that's your neural network, and for my decoder's parameters. Okay, at the very end, of course, you don't want to maximize the likelihood for one data point. You want to maximize the likelihood for your entire data set. So what we had was an evidence lower bound for one data point, and the actual lower bound for the entire data set is just the sum of n equals 1 to 10, because I have 10 data points, and then the evidence lower bound, or like the score, or whatever you want to call it, loss for every data point. So now you'll do exactly the same as what you've done in any of your previous practicals. I'll take a mini batch of samples, so I'll sample 2 or 3 images, I'll compute this loss, and I'll backpropagate through it. And that way I'll learn an encoder and a decoder. Okay, you happy with that? So here's the practical that you're going to do. The practical will take images, MNIST images, and you're going to write an encoder that takes X. And of course, there's no way I can take an MNIST digit and compress it into one number. There's just too much variability. So X will be compressed into some Z that's a lot bigger than the example we had, and you're going to decode it back into X again. And all that you'll do in the prac is you'll see how learning happens and how this encoding decoding process improves. So how do I test a model like this? Well, one way is through some visual inspection. So if my decoder works really well, I should be able to take Gaussian samples from Z, and I should be able to transform them, and they should look really nice. Essentially, that's the take-home message. If I have not learned it, I just get lots of garbage out. You'd probably also see how the evidence lower bound goes up, or the -1 goes down as you learn. Okay. That's the end of the explanation. You've done actually really a lot here. I told you what variational inference is. What's variational inference? You take a super big let's go back. You take a super big integration problem that you can't do, and you turn it into an optimization problem. So that's essentially variational inference. I told you about encoders and decoders. We also touched a little bit about compression. We talked about what it means for images to live on a lower dimensional manifold. It's like you take 16 dimensions and you encode it into 1. What else did we do? I told you about Monte Carlo methods, taking a stochastic sample and using that sample as an estimate. And lastly, we learned about the reparameterization trick, taking noise and injecting it from outside your network so that your gradients can flow through the entire network. So what I've sort of explained to you is often called VAEs, variational autoencoders, or auto-encoding variational base, depending on what your preference is. it is one of the, for the last 2 or 3 years, has become one of the key building blocks for doing unsupervised learning. For instance, there's no reason why I should take my latent code, which I call Z, and let it generate an image. I could also imagine scenarios where I have a sequence of latent codes that are transformed, and they get transformed into a time series, etc. Okay, a few more things that I actually forgot to mention that I should really tell you. Who of you wrote a single-layer neural network as your encoder-decoder? Aha, so there's some magic in your single layer. So, and the magic in a single layer is that if you have an input X, you have a one layer that goes to Z, and you have the same weights that take you back to X, and these weights are shared, then, and this is a Gaussian observation, then under the hoods, you essentially just learn PCA. There are more subtleties in here. For instance, you might change this ever so slightly and obtain a mixture of Gaussians, depending on your latent code. And there's a whole family of things. I would do a plug for an awesome machine learning researcher. His name was Sam Ruiz, and he wrote a few papers in which, these papers are from the late 90s, where he essentially explained many of the current neural network techniques that we have now, that were just single-layer techniques back then, as encoders and decoders. So if you search for him and you search for linear Gaussian models, you'd actually find the seeds of these ideas way back in the 90s as well. Okay, that was one. The second one that I want to plug is the EM algorithm. Who knows the EM algorithm? Okay, so the EM algorithm has 2 steps. The EM algorithm takes, in the E step, takes an expectation over some latent variables. So in Alta's mixture modeling example, the expectation was on your latent variable was your cluster allocation. And your M step then says, I take that cluster allocation and I decode it into my data. So you could also see this bit in the middle in some other kind of models as a cluster allocation. And then in the style of the classical EM algorithms, this component is your E step. It would take X and it would get the expectation, still with the lower bound. And the M step would then maximize essentially both of them. So you could rewrite many of these things in that famous, like, 1970s Dempster EM paper. So that's EM for you. It's also hidden in there. The next thing is maybe a comment on GANs. Someone asked about GANs a little bit earlier. I'll make only one comment on GANs because it actually deserves a whole session. And it's an incredible suite of techniques. But the one thing that is slightly open in the GANs community is this. What we managed to do in this framework is we managed to actually try, at least, to capture the entire data manifold. So in this case, our manifold was one-dimensional, because it was just 0, 1, 2, 3, or 4. And from our data manifold, we managed to generate, if this worked really well, our entire suite of images. Now, what is sometimes seen in the GANs literature is that if you were to sample from your model, you'd get a number of images that look almost exactly like each other. So it does great things in generating images, but it does not yet, asterisk, star, etc., lots of research, open research problems, it does not actually really learn the data manifold. Okay, next comment here maybe is that I probably all-conned you with this example because it's really easy. Real images don't have a one-dimensional data manifold. Also, the idea that we can take a Gaussian prior that does not have heavy tails and somehow magically transform it into real images, that actually have very heavy tail distributions. If you look at image statistics, they're not Gaussian. Maybe that assumption is also really far-fetched. Okay, so why do we do this? Why do we stick to Gaussians and not really model images of these super heavy-tailed priors, for instance? Well, one is purely computational convenience and the bag of tricks that we have. If I were to use a Gaussian prior instead of some heavy-tailed thing or something else, I can pull out this reparameterization trick and I can really do amazing things in deep networks. If I were to construct some super complicated prior here, then I can basically only train very, very small models. And I don't have access to the whole stack of forward propagating to an error function and back propagating all the way. Just a little bit of a choice at the moment. What else is hard? Okay. I told you that Z is actually a number, 1, 2, 3, 4, or 5. 1, 2, 3, 4 in this case. And that's a discrete number. So there's no reason why we should represent something that's discrete with a real continuous valued latent code. For instance, if I had a number that told you if someone was in this auditorium or not. It's just one bit of information. That's really like a latent, like a class label. Like, yes or no, there's someone in the auditorium or not. And based on that concept, you might want to render someone here anywhere in the auditorium, or if it's off, you don't want to. Okay, so that's not a real number. So that's also kind of latent structure that might be missing. There was a comment about these Zs in many dimensions being completely independent. Maybe that's not realistic, because there might be actually a lot of structure in your data that you're missing. That's also an open question. Another open question in inference is the one that I mentioned where, just bear with me for a small second. The one that I mentioned is that we employ the KL divergence to get solutions where this mass tries to fit the prior as good as it can. So there's a trade-off between two terms in my objective function. What I sometimes see if I train these models and I have a very big latent code is that not all of my code is actually used. So for instance, if I had an encoder-decoder, which I have here, if I have an encoder-decoder and I made this a 100-dimensional code, then you often find that maybe only 20 of the dimensions from this 100 is actually used, and the other 80 dimensions are completely pruned. So another open research direction, if you're interested, is finding ways to actually use all of my capacity. And this idea actually goes back, if you have a few minutes, I'll just bore you with the historical details. This idea goes back to the early 90s when the first variational methods came about. People tried variational methods for hidden Markov models. And actually, Emily's supervisor, David Mackay, wrote a really nice note on this, and he said, the observation is that if I were to really do Bayesian inference and I were to take a very, very deep code, I would make it like 100 units or 200 units, then I expect my model to use all of its capacity because it's there. But what you find in practice is that you get something called variational pruning, where many of these units are just not used. So this kind of thing called variational pruning, like not using your entire latent code's capacity, has to do with the way we cheated. And the way we cheated was to define a lower bound. So this idea of a lower bound actually penalizes Gaussians that are not close to the, that don't really capture a lot of mass underneath. It also penalizes Gaussians that are really wide, like wider than the, so you always have approximations that are way too narrow. So it's just a caveat of the way we set things up. So there might be other ways that, if you're interested in research problems, that you can find to write different kinds of encoders that don't have these properties, that don't prune dimensions away. What are other? There are also resource directions where, of course, you make this deeper. You have a whole stack of Z variables. There are also resource directions in which you try and split Z variables to have different meanings. For instance, if you have a data set of faces and you want one part of your Z variable to represent lighting conditions or the up and down pose, and you have another part of your Z variable represent the left-right pose, then maybe you can split your data set and clamp one Z and let one Z be responsible for generating up and down, and the other Z be responsible for generating left and right. Next point in that is the kind of codes that we get in here, if this is high dimensional, is really a very entangled representation of my image. It just maps it to a manifold and back again. And if I were to look at this, I mean, I can't really look at it and see any structure or meaning. So maybe if you want to do research in some other project, maybe you can find a way to really put meaningful structure in these latent codes and find a way to learn structure in them. Okay, I think I'll probably end there and ask if you have any questions for the next 10 minutes or so. Yes?
No, firstly, that was a very good lesson. I've seen this stuff before, none of it made sense. I have two or three questions. Let's say that I do this thing, I do the whole training process I've done, and then I find that I can sample nice images, right?
Yes.
Right? Oh, sorry. I find that I can't sample nice images. How do I know if the problem is with the code being small or not me having enough data? Do you want to say layers in the code, the length of the code to exactly here?
Okay, so the length of the code could be an issue. So maybe that's a good thing to try in the prac. So in the practical, you should be able to set the length of the intermediate code. So you take a MNIST digit, which is really easy. You compress it into, say, a 50-dimensional code and decompress it. You can try and set that number to 1 and 2 and 3 and actually see what the loss is. You also get a bound on the likelihood of your data. So in your code, I mean, let me just flip to the last slide. In your code, you'll get an evidence lower bound. And that's a number that should be as high as possible. So for instance, if you were to make your latent code bigger, and this bound is bigger, then of course you've done a much better job in modeling the likelihood of your data. So I guess the real answer is you should just try a large number of possibilities and see which gives you the largest bound without overfitting yourself, like looking at the test set and then tweaking and looking at the test set. So keep the test set aside, try it on the validation set. Don't do overfitting by constantly looking at the answers, because you should not do that. Okay, more questions? Yes? Yes. Yeah. On the... Oh, okay. What on earth does this sign mean, right? So it's just standard notation. So if I have two distributions, one distribution is there and one distribution is there, and I call one P and I call one Q, then the KL divergence between, in this case, Q and P would give me a number, and the number tells me how different these two distributions are. And these two bars, it's just standard notation. Of course, if P is exactly equal to Q, then the KL divergence is 0. If Q is super far away, the divergence goes up. And the divergence depends on the kind of mass overlap that these two distributions have. So that's why, if you look at the Wikipedia page, there's a big integral in there, because you care about the mass between these two. Kullback-Leibler. Yeah. Yeah. Yes.
Why is that a problem? Because I know this is a bad analogy, but it's kind of like you're using more components in PCA than you should. I mean, you're only
Okay. That's a really good question. It comes back to something that Konstantina mentioned earlier, and that's about Bayesian averaging. So the idea of Bayesian inference is that you should be able to specify codes or parameters that are much bigger or they're much larger than your data set. And then if you average over all possible assignments of codes, you should still get really nice answers. Now, you can imagine that in this averaging process over all your assignments of codes, there would be one solution in which components 1 to 3 are used and they're decoded. There might be another solution in which, legitimately, components 4, 5, and 6 are used and they're decoded. So the true answer would really use the entire capacity. I mean, we know that as a fact. But because we make an approximation, the approximation's property is just that at some point it's going to stop pruning. It's going to stop using the full capacity. It's either some people like it because they say, yeah, it's pruning things that you don't need. Other people don't like it because they say it's not in the spirit of real Bayesian inference. Yeah. Okay, we'll chat. There's lots of work in trying to not make it happen. Let me just put it that way. Yeah. What if the so that it's not smooth? Okay. So the question is, what if your data distribution is disconnected? That's totally possible as well. I'll give an example. So what would happen then in a disconnected distribution? So imagine all your x's are here and here. You just learn a really weird decoder where your prior is here for z, and it'll be a function that for all of those z's, it's really going to morph it into stuff on that side, and for all the z's on that side, it's going to morph it to things on that side, and maybe somewhere in the middle, it's really going to look like that, and it's not going to morph or decode it to something in the middle. So actually, it's a little bit like the MNIST data set which you'll use. Like you've got digits 1, 2, 3, and there's like a massive void of unused X space in between them. Yeah, so having clusters in your data is not a problem for this. Yeah.
Yeah, the error function, way back the way at white noise. I was wondering, it obviously changes the distribution, right? The white noise doesn't either end in order to be able to do the value there.
Okay. You mean in this reparameterization trick?
Yes.
Okay, so this actually does not, this is important, this does not change the distribution. So I can either write, I can either draw Z from a Gaussian with some mean and some variance, or I can draw a sigma from a Gaussian with 0 mean and a variance of 1, and I can say Z is equal to the mean plus epsilon times sigma. And these two processes will have exactly the same distribution. So that's why this whole reparameterization trick works. Between these and GANs. Okay. So from a very high level, GANs also has two networks, and it has a generative network that's going to try and generate images. It's actually going to try and classify between true and false images. And then it's going to have a network that's going to try and fool the classification network. Okay, so it does not start with the assumption of having some manifold and decoding it into images. For GANs, you can probably get much nicer images. The community is also a lot bigger than it is at the moment for guys that are doing this. It does not mean that this is the wrong approach. It just means that we probably need a much more powerful hammer to do this. Do you mind repeating the question? I'm not sure I get the question. You want to put two of these in a GAN? I'm sure it's worth a try. Yeah, it should be possible to put this in a GAN. But let's take this question offline because I'm not sure I exactly got the question. If you don't mind talking afterwards. Yes?
Hi, thank you again for an awesome talk. Could you tell us how does this compare to like a naive autoencoder where there's no, where it's just a neural network and you train it by some reconstruction error?
Oh, okay. So the difference is that a naive autoencoder would not have a probability in the middle. Okay? So you basically just encode something and you decode it end to end. So you basically just construct a neural network where you have an image as input and exactly the same image as output, and you have a bottleneck in the middle. This says that I'm going to give my bottleneck a certain predefined shape, which is Gaussian, for instance, and it allows me then to start with the bottleneck and then decode it, whereas otherwise I would not be able to start with the bottleneck. So the nice thing here is that I really actually model the density of images. So if I were to sample images, all I had to do was to sample Zs and then decode them. And that would generate images from that should look like my data set. Whereas if you had an encoder that just had a latent code, like you can't really start in the middle, can you? I think that's my view. Yeah, Steve. Yeah. We've trained it on like 256 images. My one student has done speech modeling with this, where speech is a high-dimensional signal, and you learn to generate speech from like a random process. So I mentioned that your Z doesn't have to be just for an image. It could be a Z that progresses and that generates a time series as well. As to the kinds of architectures, as much as you can push onto your GPU, I guess. Yeah. Like, how would you do that, or how would you set your? Okay, the question is, how would I structure the network such that I get something image-like out? You'd probably use a convolutional, deconvolutional architecture. That's the first answer. Second answer is for really high-dimensional, complicated images. If I were to feed in an image of this room, and I encode it, and I actually get an image of this room out, I would almost win a Nobel Prize. It's a really, really hard problem. So it's not just a structure problem. It's like finding the right ways to optimize it, to train it, to find the right architectures, number of layers, making sure that nothing gets lost or pruned along the way. Also having a likelihood that captures your image statistics. So for instance, images are not real valued numbers. They're RGB, they're between 0 and 255. You don't actually have a uniform distribution over all RGB values, so that's a problem. Other one is maybe thinking of ways to make your image generation process autoregressive. So you don't need to have an MLP or a ConvNet that decodes it. You can have a much more complicated network that does your decoding and encoding. But there's no golden bullet answer. Okay, Ben, you had a question as well.
Just in terms of independence of the Z's that you sample for your reconstruction, you
Okay. So the question is, what if Z was a time series? Okay, so I'll backtrack for this, and then we'll finish. When I ran through this slide deck with one of my friends in DeepMind, his first question was, oops, and if you bear with me to get the very first page, his first question was, well, what is this data series that I'm giving you? You are. Is this a time series, or is this a set of independent images? And if it was a time series and there was some temporal correlation between them, and this one was actually t equals 1, t equals 2, t equals 3, t equals 4, then of course you can't model it as independent things. So what you need to do is you need to think of a way to essentially marry the techniques you learned in Stefan's recurrent networks lecture with these techniques that make things stochastic. So in the RNN talk, you had a hidden state, and the hidden state was deterministic. In this case, you have a hidden state, and the hidden state is stochastic. In the RNN talk, you had a hidden state, and you could view it as deterministic. You could view it as stochastic with a delta function, like a Gaussian with zero variance. And there are ways to extend that to be a stochastic recurrent neural network. Why it's harder is because you open a massive can of worms. And the can of worms is this. The can of worms is that to get this encoder-decoder to work, we had to solve an integration problem, and we solved it with sampling. So we had to sample for one image. I had to get Z, sample, and decode it. If this was actually time series, I would have to take an image, encode, decode, sample, then generate it, like figure out how to generate the next image, encode, decode, sample again, encode, decode, sample. So what you have essentially, if you want to compute this in TensorFlow, is this chain of samples, where if you have a chain of samples, you either have a variance that either blows up or shrinks to zero. So that becomes very, very hard to train. And then the odds of having this chain of samples accidentally hit the final sample that generates a nice final image or a nice sequence of images, that just becomes smaller. So the problem becomes exponentially harder. That's almost all I can say about it. Maybe one more thing there. You don't have to make this chain a neural network. You can use very, very old-style methods from statistical inference. So I mentioned that this one-layer encoder-decoder is essentially PCA. Now, we can compute all the PCA solutions analytically. It's just you look in Wikipedia, you write down the answer. If we had a temporal series, we can also analytically write down the answer for the time series equivalent of PCA. So who of you have heard of the Kalman filter? Yeah. So if you didn't have a deep network, but just a linear transition, you could use a Kalman filter as something that captures your temporal correlations, and then plug your deep network somewhere else. So that also seems to work for some problems. Yeah, that's almost all I can say about that. It's like a really crazy open research area.